lectures to be videoed easily and readily, then I see the classroom lecture just dying, right? Because from the student's point of view, if you can rewind, it's just so superior than just missing something when you don't follow it the first time and the only time, because the classroom professor, the waged professor as I call him, just keeps going on. So if you miss it, you've really lost it. So that's a major inferiority of the techniques of the wage prof, the classroom teaching. Okay, now the only if, now a bit of discussion, right? Now the only if, that's the other way, so that'll be if P then Q. Now why is that? P only if Q. So the only way you can get P is by having Q. Right? So if you do have P, you must have had Q. So if P, then Q. So if P, then Q. Right? So in other words, this time we're proving it from the left-hand side. So we're assuming that A and B, these two natural numbers, are prime, and we have to prove this. Woo, woo. That's going that way is not obvious at all, right? So I take my hat off. That means I respect highly the brilliance of the pure mathematician who created this proof in the first place, because it's really quite ingenious, but not easy, not trivial. Okay. So before I launch into it, a little bit of discussion to try to. As usual, when you start a proof, you need a direction, some clue, some indication that it might be a fruitful way to start looking. So, given A and B are relatively prime, so no common factors, how on earth do you prove this? From left to right. How do you prove that? So, what are you trying to do? You're trying to show that there is, that's what this mirror reflected capital E means there is, so, or there are. So there are integers x and y, so that this is true. So let's, here's one approach. Let's try to show, see A and B are given, right? And we have to show that there are these integers x and y such that this equation holds, so that ax plus by equals 1. So let's concentrate on this expression and try to prove that it equals 1, that there are an x and y so that ax plus by equals 1. So let's play with this ax plus by, and try to show that you can find an x and a y so that ax plus by is 1. Follow that? If not, rewind. Okay? So this proof, this only if proof, going from left to right, is going to involve playing with this ax plus by. Now, this x and the y, they're just integers, right? So, I mean, how many expressions are there of this form? Will there be an infinite number, right? I mean, A and B are fixed, they're given, okay? But you could have any x and any y, and we're trying to prove that this equals 1. But we haven't proved that it's 1 yet. We're going to have to find constraints and things that force us to say that there is an x and y such that this does equal 1. So let's concentrate on this. So that's an approach. So let's form, and here's the creative leap now, right? Here's where the brilliance, the creativity of the mathematician who invented this comes in, shows itself. So let's create a set. We'll call it S, and it's the set of all these, for all possible x and y's. So you have ax plus by such that x and y belong to the integers. Okay? So we're concentrating on this, and we're creating a set that are all possible these. So for different values of x and y, your different integers x and y, you'll now we know the number. Well, a and b are given, right? We're told that they're relatively prime. So we assume we know a and b. So this is the set, an infinite set of numbers that take this form. Right? Whatever a is or b is, you plug it in here, and all possible x's and y's, you plug in your two values here, and you'll get a number, ax plus by, and all possible numbers, all possible solutions to that, that's your set, S. Okay? Right? Now we can use the division algorithm. So here's the next creative leap, and you may be saying, oh, what the hell? Where did this come from? It works, right? When you're a pure mathematician, researcher, you can stare at a blank sheet of notepaper all day and not write down a thing because you didn't have a good idea. That happens. That's the nature of the beast, right? Pure math. That's quite a common occurrence. So finding proof sometimes not easy. All right. So second creative leap. Let's use the division algorithm. That's why it's here, right? For well, actually, I need to go backtrack one. Now of all these values, let h be the smallest positive member, we'll say member, the smallest positive member of S. Okay? So these will have all kinds of values, some positive, some negative. It depends on the, if your x is a negative integer and y is a negative integer, and let's say a and b are positive, then this whole thing will be a negative integer. Okay, so you'll have positive and negative possibilities here, results. So let h be the smallest positive member of this set. Okay, the smallest positive. Now we'll use this later. This will become one of the constraints in the proof, right? So this idea of using a set of all possible values like this here, and then we're going to we let h be one of these, and it has the property that it's the smallest positive member of this set. So h is one of it has h has this form, ax plus by. H is a member of this set, so therefore it has this form where the a and b are given, but we don't know what x and y are yet. Okay, all right. Now so we have h. Let's say. Now let's express h using the division algorithm in terms of, well, let's express a actually. Let's express a in terms of h, right? So using the division algorithm, a can be written in this form. So a is of the following form: q h plus r. Right? Now I've rubbed it out from before, but remember the division algorithms. You can take two integers, let's say a and h, and you can express the one in terms of the other of this form. Now r here, r will be less than h, and greater or equal to 0. Okay. Let me get rid of that. Right. So R is your remainder or residue, same thing. Okay. So R will be less than H. Okay. So it's greater or equal to 0 and less than H. Okay. So that's from the division algorithm. All right. Now, next step. What is H? It's of this form, right? Because we've said that H is a member of this set, so it has to take this form. Now we don't know what X and Y are, but let's just say that H is of this form. So H is A X naught and B Y naught. Right? We just assume that that's what H... There must be some... if you know A and B, then there must be some X and Y, X naught and Y naught, that gives you this value H that is the smallest positive, of all these numbers here, right? So let it be that. Now, interestingly,